Okay, so it's a great pleasure to have Dima Sinapova here from Chicago, talking in the, well, combined Oxford and Bristol logic seminar. So Dima is going to talk to us about iteration, reflection, and singular cardinals. Dima, please.
Well, thank you, Philip and Joe and Sam for inviting me. Let me start by sharing. All right.
Good. Better still. Yeah.
Yeah, so I'll be talking about some joint work with Alejandro Poveda and Assaf Rinot on iteration, reflection, and singular cardinals. So let me start with just some two general motivating questions that in set theory. So one is, what constraints does cardinal arithmetic impose on combinatorial principles? And another motivating question for our results is the question of, can we force compactness and non-compactness properties simultaneously? Now, what is compactness? Well, compactness, that's the phenomenon where if a property holds for all, I should say here, strictly smaller substructures of a given object, then it holds for the object itself. And in general, it follows from large cardinals. Now, a key compactness property that will be the focus of this talk is as we know it very well, stationary reflection. Okay. So let me just do a little bit of crash course on what we know about stationary reflection. Recall the definition. If we have a regular cardinal mu, a stationary subset tau in mu reflects. If for some alpha less than mu, t, not tau, t intersection alpha is stationary. And reflection mu is the principle that every stationary subset of mu reflects. So as a good compactness property, stationary reflection follows from large cardinals. For example, if kappa is measurable, one can prove that reflection at kappa holds. You can even do more if you assume stronger large cardinal hypothesis. So if mu is bigger than kappa and kappa is mu supercompact, then you have reflection at all stationary subsets of mu of points of cofinality less than kappa. Now, just a quick note, because this will come back later, the reason we restrict to points of cofinality less than kappa is because you need the cofinality to be below the critical point of your embedding witnessing the mu supercompactness of kappa. Okay, this is this remark. And so an anti-example of stationary reflection is very well known. If kappa is regular, then kappa plus intersection cof kappa never reflects. So in particular, reflection at successors of regulars always fails. So in other words, when we talk about reflection of a cardinal, I mean, the only two situations in which it makes sense is if the cardinal is a successor of a singular or if the cardinal is inaccessible. Okay, and here we'll concentrate on the successor of a singular case. Okay, so now a little bit more about stationary reflection. So it's a key compactness property. It follows from large cardinals, as mentioned in the last slide, and actually needs large cardinals. It fails at, so this is just summary, fails at successors of regulars. Now, remember, one of our motivating questions was, can we force compactness and incompactness properties at the same time? So stationary reflection is a key compactness property. Now, what about an incompactness property that we're interested in? Here, this will be the failure of the singular cardinal hypothesis. So let me say a little bit more about this. So what is SCH says, the singular cardinal hypothesis? Just to recall, it says that if kappa is singular strong limit, then 2 to the kappa is kappa plus. So it's a parallel of CH for singular cardinals. And again, now let me recall the two questions I started with. One was the effect of investigating the effect of cardinal arithmetic on combinatorial properties like stationary reflection. And the other one is, can we force compactness and incompactness properties at the same time? And it turns out that looking at SCH, I should say failure of SCH in the context of stationary reflection, addresses both of these. So this is why we're interested in looking at those two principles, see whether they can coexist, failure of SCH with stationary reflection. Because it's like a good kind of test, like a yardstick on addressing both of these two main questions. Okay. So now, in the next slide, I want to talk about some of the tension between failure of SCH and stationary reflection. So recall this is the definition of SCH. Kappa singular strong limit implies 2 to the kappa is kappa plus. It's a parallel of the continuum hypothesis for singular cardinals. And some famous facts about SCH. So due to Solove, it holds above a strongly compact cardinal. Due to Magidor, one can force the failure of SCH, but need large cardinals. And also note that the failure of SCH is an anti-compactness property. So why is that? What do you need in order for SCH to hold? Remember, compactness was if something holds for all strictly smaller substructures of an object, it has to hold for the full object itself. But now to have the failure of SCH, what you need is some cardinal kappa such that the power set function below kappa is small, but it blows up at kappa. So this is, a canonical incompactness type principle. And now let me state the particular question, which I'm going to focus on here, is can we get the failure of SCH at kappa for a singular cardinal kappa together with stationary reflection at kappa plus? So I'm going to start with some old history about this problem. So let's take the first, our favorite singular cardinal, Aleph-Omega. So what happens there? Well, I'm going to start with two classical results of Magidor. So from the 70s, he showed that starting with a supercompact cardinal, one can force the failure of SCH at Aleph-Omega. And what was Magidor's construction? Well, so he used the Prickry type forcing, a supercompact Prickry type forcing. And let me just note that sometime later, by works of Gittik, Mitchell, and Woodin, the large cardinal hypothesis was optimally reduced to a measurable kappa of Mitchell order, kappa double plus. But so we know that SCH can be forced to fail at Aleph-Omega. Now, what about stationary reflection at Aleph-Omega plus 1? Well, this is another classical result of Magidor from the early 80s, that if you start with omega many supercompact cardinals, one can force the stationary reflection to hold at Aleph-Omega plus 1. And what is this construction? Well, so you start with omega many supercompact kappa n's, and it's just a very nice forcing, simply an iteration of Levi collapses to make to collapse cardinals between the supercompacts and make the supercompacts into the Alephs. So now, going back to our question from the last slide, well, just even at, whether we look at kappa or at Aleph-Omega, can we get the failure of SCH? So can we combine these two types of results? Get it both at failure of SCH at kappa together with stationary reflection at kappa plus? And it turns out the answer is yes. So let me first talk about some general kappa high up, not necessarily Aleph-Omega. And then I'm going to talk about particularly what happens at Aleph-Omega. So any questions so far about some of the background? Okay. All right, so this is our first theorem, and all of these results are joint work, as I mentioned, with Poveda and Rinot. So it turns out that the answer to this question is yes. And this is our first theorem. Suppose that we have an increasing sequence of am I saying that this is super compact cardinals? There they should be, okay. Oh yes, kappa n, an increasing sequence with limit kappa such that each kappa n is kappa plus super compact. Then there is a forcing extension where SCH fails at kappa, stationary reflection holds at kappa plus, and actually a slightly stronger version of stationary reflection holds, namely simultaneous finite stationary reflection, which here at kappa plus, which here we denote as reflection kappa plus less than omega. Which means that for any finite collection of stationary subsets of kappa plus, there is some alpha such that all of them reflect for this alpha. Okay. And let me just note that in the context of this theorem, that type of reflection is optimal. Namely, you cannot hope to get simultaneous reflection for omega many sets at kappa plus if SCH fails at kappa. This is, I'm not sure who this fact is due to, so maybe Solvay. If kappa is singular and kappa is omega, then reflection kappa plus omega would imply SCH. But so what we get is SCH fails at kappa and finite simultaneous reflection at kappa plus. So before I go into some of the ideas that were behind the proof of this theorem, let me give like some history and remarks. So yes, originally, like a long time ago, this was partially done, or at least claimed by Assaf Sharon, but there was a gap in the proof. And more recently, maybe a year or two ago, independently, Omer, Yair, and Spencer obtained a similar result, stationary reflection for one set, but maybe in their constructions, it's also for finitely many, I'm not sure, and not SCH with a very different proof. And looking at the schedule, I think you guys will be hearing from Spencer maybe next week. So he will get to tell you about their construction, which is also very nice, but it's quite different from ours. Okay. And now, what does our construction use? Well, so what are my talking points? First, we want to analyze, use an analysis of reflection properties in Prickry extensions in general. Why is that? Because anytime you're talking about failure of SCH, willy-nilly you have to have some Prickry forcing. Right? So what we want to do is analyze what happens with reflection after you force with Prickry type forcings. And it turns out that there is like a uniform analysis to that. All right. No. Okay, yes. And more precisely, we want to analyze which sets do not reflect. And what do we do with them? Well, it's easy. We want to kill those sets in an iteration, which is like a Prickry type style iteration. Okay. And so I'm going to be describing an iteration. Let me tell you what will happen at step 0. We will start with something called extender-based forcing. I'll talk a little bit more about it in a few slides. But for now, let me just say it's a Prickry type forcing, like a diagonal Prickry type forcing due to Motin and Menahem from the 90s, I believe. Okay. So let me talk about the first one, what happens with Prickry forcing, reflection under Prickry forcing type extensions. And the reason we want that is, as I mentioned, Prickry type forcing is the tool to violate SCH. So going back to that Magidor's original result about failure of SCH at Aleph-Omega, the type of forcing he used was super compact Prickry forcing. So let's analyze reflection in these Prickry extensions. So let's start with, the one example I mentioned. Well, if you want to combine those two properties, the first thing to look at is, well, what happens with reflection in Magidor's model? And it's not that hard of an exercise to see that reflection will fail. And if you look a little bit further, one can see that in general, if you just force with a Prickry type forcing, reflection will fail almost no matter what your Prickry type forcing is. So let's see why. Why is Prickry type forcing so unfriendly to reflection? And as a warm-up, I'm going to talk about stationary reflection in the vanilla Prickry extension. So let me motivate why I'm going to talk about this a little later. I want to tell you how we deal with reflection in our Prickry construction, which is a lot more complicated, but it turns out that some of the ideas are simple enough that they can be presented even talking about the simplest case. All right, so I have a slide on vanilla Prickry in case somebody has forgotten what it is, but so let me go over it very briefly. Okay. So let P be the vanilla Prickry forcing. It uses a normal measure on kappa, so kappa is measurable, and the goal is to add a cofinal omega sequence through kappa. So let's fix a normal measure on kappa. Now, what are the conditions? The forcing conditions are pairs S and A, where S is a finite increasing sequence of ordinals in kappa, and A is a measure one set. And the ordering is given as follows. So S1, A1 extends S0, A0, if so S1 N extends S0. The difference between the two is our points in the measure one set A0. And the measure one set of the stronger condition A1 is a subset of A0. So in order to take an extension, you increase the S here is something I'll refer to as the stem. You increase the stem by using points of your measure one set and then shrink the measure one set. So the generic for this object, you take a generic for this object, then what is your omega cofinal sequence that's added through kappa? Well, you just take the union of all the S's, all the steps. So in this way, each condition here, each condition SA, the first coordinate contains some finite information about the generic Prickry sequence that will be added. And the second coordinate, the measure one set, is the constraint. It tells you how S can be extended. And as I said, for a condition as follows, the stem of the condition will be the first coordinate S. Okay. And moreover, we have this nice characterization of genericity that the cofinal sequence, any cofinal sequence alpha n less than omega is generic if and only if it meets every measure one set on a tail end. Okay. So I also mentioned, I also want to mention that again, given a condition P, a Prickry condition, the length of P refers to just the size of the stem. And I'll be using that later. So now what happens even in the vanilla Prickry extension to reflection? Okay, well, let's try to see how much reflection we can possibly prove. Or we cannot prove. So right away, we have the same problem as earlier when you look at successors of regular cardinals. So know that if kappa is measurable in V, then reflection at kappa plus would fail in V. And it turns out that is still the case in VG when G is P generic. So in particular, in V followed by a Prickry at kappa, the stationary set kappa plus intersection points of cardinality V kappa does not reflect. And because it didn't reflect in V, so that's part of the argument. But on the other hand, not always lost. You could get some reflection. And in particular, if you start with kappa being kappa plus supercompact in D, then you can prove that every stationary subset of the other possible cofinalities will reflect. It's kind of a dichotomy here. And this proof uses the fact that every stationary subset of kappa plus of V cofinality less than kappa reflects in V. So, and it turns out that the proof of this this part too is actually kind of instructive into what we do later on. So I'll go over some of the highlights. So how do we prove this? That every stationary subset of kappa plus intersection cov V less than kappa reflects in the Prickry extension. So let G be generic for the vanilla Prickry. And so this is the theorem / lemma I want to show. And let me mention, I believe originally this is due to maybe Magidor and Shello. Okay. So what is the proof of this theorem? Well, let's fix a stationary subset in kappa plus of cofinality V less than kappa. And now the idea is, so this is a stationary subset, T in VG in the Prickry extension. And now we want to go back to V because it's in V where we have reflection. So remember, we want to show reflection in VG using that we have reflection in V. So somehow from the stationary set T, we have to define sets in V. And we define them as follows. For every Prickry stem S, let T sub S be the set of all alpha such that some Prickry condition P with stem S forces alpha is in T dot. So you can think of the T sub S as the traces of T corresponding to a given stem. Now note that these sets, each T sub S is a set in V. So if it is stationary, it would reflect. And it turns out that densely often, those sets T sub S are stationary in V. And now, since kappa is supercompact in V, now back in V, kappa is supercompact. So whenever stationary, T sub S reflects. And the final point in the argument is to conclude, to show that your reflection for the traces gives you reflection for the actual set T. Okay, that is T sub S reflects, then so does T. It takes an argument. It's a nice argument not to. It's very well written in, for example, Scarce Squares and Stationary Reflection by James Matt and Menahem. Okay. And the reason I went over this theorem is something like this, but more involved Prickry context is what we use later. Now, let's go back to the non-reflecting sets. Well, the problematic cofinality is called V kappa. Right? The sets that so these are the sets that don't reflect, and this is what we wanna kill later. Okay. And so far I've been talking about a vanilla Prickry, which kind of models a Prickry type forcing that singularizes kappa. For our notation iteration, we'll be actually using, as I mentioned earlier, a type of forcing that's a Prickry forcing, but already starts with a singular kappa. However, it turns out that there are a lot of similarities, whether you singularize kappa or not. So let me talk now about the Prickry type forcings that do not singularize cardinals. And now I can say a little bit about this extender-based forcing, which is what we use in our iteration, EBF. All right. So what does the extender-based forcing do? So it starts with so remember, the vanilla Prickry forcing just starts with a measurable kappa and adds an omega sequence through it. Here, we want to start with kappa, which is already a limit of some strong cardinals, kappa n less than omega. The kappa n should be strong. And EBF is a Prickry type forcing, which in order to violate ICH at kappa, aims to add kappa double plus many Prickry sequences through the product of the kappa ends. Okay. And I did not include any further definition of EBF. I just want to say that, well, just like regular Prickry forcing, vanilla Prickry forcing uses one normal measure in order to add one Prickry sequence. Here we need many measures to add the kappa double plus many Prickry sequences, i.e. we need an extender. This is why it's called an extender-based forcing. So this forcing uses an extender on each kappa n to add those kappa double plus many Prickry sequences through the product, and then they'll guarantee SCH fails at kappa. Okay. What happens with reflection when you do forcing with EBF? So let PB extender-based forcing, and I didn't say this, I'm sorry, but suppose in V each kappa n is kappa plus supercompact. So we need the supercompact hypothesis. Let me actually make a note to fix this. Okay. Okay. And then in VP, if we start with each kappa n being kappa plus supercompact and force with extender-based forcing, again, we have reflection at kappa plus as long as you restrict to this time cofinality greater than omega. And the argument in spirit is similar to the argument I showed you guys from the previous slide, the outline of the argument. So it's a different argument, but same in spirit. So of course, there's some non-reflecting stationary sets here too. And this time, the non-reflecting stationary sets are of countable cofinality. And so what we aim to do next is generalize both of the above cases, something like EBF and something like whether it's a Prickry forcing that singularizes kappa, you can think of vanilla Prickry, and analyze what are the non-reflecting sets. Okay. And since I want to analyze both of these forcings together, what Assaf and Alejandro and I ended up doing was defining like a category of Prickry type forcings, which we call sigma Prickry.
So and, can I ask something?
Yes,
yes. Is it possible to explain to us a little bit more what extender-based forcings are like? I mean,
yeah, yes. So, yeah. So the let me first tell you what the goal of an extender-based forcing is. So we have. Okay, so this is the setup, an increasing sequence of they should be strong cardinals kappa n with limit kappa. And your goal is to, you're not singularizing anything, is to just directly violate the SCH at kappa. How to do that? Well, by adding, to make 2 to the kappa be kappa double plus, you want to add kappa double plus many omega sequences through the product of the kappa n's. Okay, so for each sequence, you need a normal measure. So here you need, kappa double plus many. They're not going to be normal. Kappa double plus many measures. Now, measures on where? Well, the only guys that can have measures on them are the kappa n's. Okay, so what the assumptions are is you start with, for each kappa n, you start with an extender on kappa n of length kappa double plus. And you use those extenders, so they're omega extenders, each of length kappa double plus, to add kappa double plus many, omega sequences, so I call them Prickry sequences, through this product, where suppose you pick your favorite index. Let's say pick the normal measure for each of those extenders. This gives you omega many normal measures. Well, the Prickry sequence corresponding to that sequence will get into every measure one set on a tail end, but it's kind of diagonal. then pick, I don't know, the alpha measure of each extender for some alpha less than kappa double plus. Then the alpha Prickry sequence will be generic with respect to those measures UN alpha and kappa n. The actual definition is, it's a little cumbersome to write, but the best way to think about it is, well, I want to add kappa double plus many Prickry sequences. I need kappa double plus many measures, of course, on each kappa n, and then you add them diagonally. And again, every condition has two parts, a stem, so a finite part, which gives you like initial segment information of all your kappa double plus many sequences, and measure one set / constraining part. I don't know, should I say something else?
No, fine. What kind of closure conditions does it have? I mean, come on.
The closure is that a condition of length n is kappa, the direct extension order for conditions of length n is kappa n closed.
Okay.
So the Prickry property holds, and for example, to show that no bounded subsets of kappa are added, suppose I want to show that no bounded subsets are added, no subsets are added of kappa 17. So I start a condition of length at least 17, apply the Prickry lemma to it, and use the direct extension is kappa 17 closed to complete the.
Dima, could I ask a question? So maybe it would help if you just clarified in a more concrete, elementary way. What does it mean to have a Prickry sequence through that product? Is it a omega sequence of sequences each going to kappa n, or is there other kinds of reflection happening on those sequences?
It's what in the first thing you said.
Okay, so a Prickry sequence through the product is just an omega sequence of Prickry sequences that are getting taller and taller through those kappa n's. Is that what you mean?
So, and so that they're generic for
right.
Sequence of measures given by those extenders.
Okay.
So, for example, yeah, the very the most I guess special Prickry sequence of those kappa double plus many is the one corresponding to. So each extender has at least exactly one normal measure, right? If you take the sequence of those normal measures, the 0th Prickry sequence will correspond to them. Meaning that for every omega sequence of measure one sets, for all large n, the Prickry sequence gets into those sets.
Thank you.
I wish I could write something, but I didn't hook up the right device. But maybe at the end I can, I'll have some time for questions where I can open up my whiteboard.
Fine. Great. Thank you.
But yes, it's important that, Philip, I'm also glad you asked me this, when you increase, when you fix the length of conditions, you get that direct extension order has good closure, and this closure increases as you increase the length. This will be used later. Okay. So next in this definition of sigma Prickry forcings, we wanted to kind of categorize the properties, so to define a type of poset that will combine, that will apply to both Prickry forcings that singularize kappa, EBF forcings, diagonal supercompact Prickry forcings, etc. So this is the definition. P is a sigma Prickry forcing with respect to a non-decreasing sequence, kappa n less than omega. Now that I want to allow for both singularizing or non-singularizing. If, and this is very important, exactly what I was just talking about, when you restrict P to a certain length, so this is like called, I'm going to refer to this a direct extension order where conditions increase in strength but not in the length, you have your forcing is kappa and directed closed. And maybe some of you can see why we would want that in the future. So the good thing about kappa and directed closed forcings is that if kappa n is Laver indestructible, it remains super compact after such a forcing. So this first item will be instrumental in later on proving we can get reflection. And then part 2 is a more technical condition who people familiar with Prickry type forcings will maybe recognize. So for every condition P, there is a set of what we call weak step extensions of P, which we denoted by W sub P, W standing for weak, such that the weak step extensions of P have size less than whoever becomes the successor of kappa. And for each kappa, those weak step extensions restricted to some length kappa is a maximal anti-chain below P. So this is, if you've had the pleasure of proving Prickry type lemmas in your life, this is usually how the argument goes. You get your condition, you look at possible weak step extensions, you ask, oh, is there something direct extension below it that forces P, etc., etc. Okay. So 3 is complementary to 2. If Q is stronger than P, then this is what I meant by maximal anti-chain. Then there is some unique weak step extension P prime in W sub P, weaker than Q of the same length. So if you look at vanilla Prickry, so if you take some condition stem S and then measure one set, the weak step extensions will be indexed by finite increasing sequences of the measure one set, which you can add on to your stem S. And of course, then there will be kappa many, which kappa is less than the final successor, the successor of kappa. And no, it's so if you have stem S and a measure one set A, if you want to strengthen this condition to increase the stem by one more point, how many incompatible ways of doing this? Well, it depends on, for every point in your measure one set, you can tag it along to the stem. This will give you W sub P restricted to the first length. I hope that makes sense. Okay. Maybe, okay. And we want the strong Prickry lemma to hold. And we also want a strong form of the mu plus chain condition, witnessed by kind of an absolute function, which witnesses. So what we really want is mu linked, this poset. So just to, I mean, it's a long bullet point, but just to sum up, well, we want the direct extension to be closed. We want the Prickry lemma. We want good mu plus chain condition. And some of you may wonder why mu plus and not mu. Well, it turns out that for the extender-based forcings, the chain condition is the double successor, not the successor. Okay, and there's some more technical properties that I'm going to skip, but it's like the closure, Prickry chain condition. Okay. And now we can we prove this kind of abstract lemma. If P is above and the kappa ends, I should add this, and the kappa ends are super compact, then we have reflection for all sets in kappa plus of that cofinality between omega and kappa. Okay. And now what is the proof of this lemma? Well, again, morally, it goes back to the idea of how we proved reflection in the vanilla Prickry. So let's recall fixing a name for a stationary subset that we try to prove, we want to prove reflects. We consider those traces, the T sub S's for each step. Okay, and by reflection in V, each T sub S when stationary reflects. And from then you argue, it takes an argument, but you argue that T reflects. Now, this generalizes to other Prickry forcing, allowing us to prove the previous lemma of the previous slide with just one difference. Now, instead of the stem, because there is no, we don't really want to commit ourselves to what the stem is if you're just talking about a sigma Prickry forcing. we look at the traces by fixing the length of conditions. Okay. Let me be more precise what I mean. Let P be a sigma Prickry with respect to some increasing supercompact sequence kappa n's with limit kappa. Let Pn be just P restricted to length n. And let T dot be a name for a stationary subset of kappa plus. So now let's look at those traces. Let T dot n be the set of O alpha such that there exists P in Pn forcing alpha in T dot. So instead of looking at traces indexed by stems, now we look at traces indexed by lengths. Now that, so this is a slight abuse of notation, but each Tn can be thought of as a Pn name, right? Because you can think of each Tn as, pairs alpha T such that P forces alpha in T and the length of P is n. So in particular, if I have some generic for Pn, and here Vpn just denotes a generic extension for Pn of some generic that I don't want to specify, then we can interpret this T dot n. So the traces for each length n are in this Vpn. And now recall what was the #1 item of the definition of sigma Prickry forcing is that this guy Pn was kappa n closed, directed closed. So if Tn is stationary, it must reflect. Okay. Because we started with, well, I should say destructively supercompact, Pn is kappa n directed closed, so we know that those traces, as evaluated in a generic by Pn, reflect whenever stationary by the kappa n directed closeness. And if that happens often enough by a somewhat more involved argument from the vanilla Prickry forcing, but again, morally similar, we can prove reflection for T. So to sum up now the outline of the argument, we actually have the following lemma. If so here what do we have, that if the given a stationary set T, if we look at its traces for a given length n, if they themselves are stationary often enough, then T will reflect. So the contrapositive is this lemma. If we have a name for a non-reflecting stationary set, then for unboundedly many n's, the T dot n's are non-stationary. And this is really kind of the key part of the analysis as to which, so what was one of our goals, to figure out which sets are the non-reflecting. Well, if something is non-reflecting, then it must be of the form that its traces are non-stationary. Okay. All right, so, okay, so what do we want to do with non-reflecting sets? Well, we want to kill them. And how do you kill a stationary set? By adding a club to it, through the complement of it, right? What is the usual problem of trying to add a club through the complement? Well, you may get into trouble, you may collapse cardinals, etc. Now, here what will save us, just trying to give the intuition, is the fact that at least we know that the complement of the traces contains a club. So we'll be adding a club through the complement of this T by using that, often enough, for all large n, the points of that club will actually be disjoint from the traces Tn. And the reason that can be achieved at the closure steps is because the Tn's are non-stationary. Okay. So killing one reflecting stationary set. This is our just the lemma of how you kill one of them. Let P be a sigma Prickry forcing with respect to increasing supercompacts kappa n's. Let T be a non-reflecting stationary subset of kappa plus intersection cuff less than kappa. So this is our working lemma. Then there is a sigma Prickry forcing A, which we call A, piece of T dot, such that, so A projects to P. A forces that T dot is non-stationary. And again, the point here is that A itself is sigma Prickry. So this will give us the successor stage in our iteration. Given some sigma Prickry type forcing P, we can construct something that projects to it with a successor step, which is still sigma Prickry, so cardinals are preserved, but it destroys the stationarity of this non-reflecting set T dot. Okay, and as I mentioned on the previous slide, we want to force a club disjoint from T, but in a Prickry style way. And to do that without collapsing cardinals, it's we use the key assumption that T dot is non-reflecting, and therefore its traces are non-stationary. So let me say very kind of informally, think back to the forcing of just, adding a club through forcing. What are your conditions there? If you want to add a club through kappa plus, conditions will be, let's say, closed bounded subsets of kappa. The ordering is end extension. And where could you get into trouble? Well, possibly, it's not gonna be closed, but is that when you have, let's say, some sequence of this end extension closed bounded subsets, the supremum of their maximum may not be in the complement of the set you're trying to kill. This is very roughly speaking what one has to deal with. Well, here we require that, this APT uses more than one, just a bunch of these closed bounded subsets of kappa plus, and require that their maximums are actually disjoint from Tn. And the fact that the complement of Tn contains a club is what allows us to catch our tail, so to speak, at limit stages. I know this is vague, but maybe it makes some intuitive sense. Okay, so, and preservation of cardinals follows from the poset being sigma. So the key point of this lemma is that you can add a club to kill it has to be a non-reflecting stationary set in a Prickry way. Okay, so now we want to iterate this because, of course, we have more than one non-reflecting stationary set. By a bookkeeping function, we actually have, kappa double plus main. So we're going to iterate this. So this lemma, you can think of it as our successor stage, kappa double plus many times in an iteration with support kappa. Okay, so, and when we did this, we actually proved like an abstract iteration theorem, which then we later applied to our specific case. So what does the abstract one says? Well, informally, we can iterate the above kappa double plus many times. And here is the general theorem. Suppose that kappa n is strictly increasing with limit kappa, and we have Q is a sigma Prickry forcing with respect to the kappa n's. Suppose also that we have somebody has given us an operation to pull up whenever we do successor stages from P to Z to APZ, where whenever you plug in some sigma Prickry forcing T and some element in H kappa double plus, you get the machinery spits out a sigma Prickry forcing, let me call it APZ. Then we can iterate this. Is the conclusion of the theorem, i.e. there is an iteration P alpha less than or equal to kappa double plus, such that P alpha is your initial guide Q, P1 is your initial guide Q, each P alpha is sigma Prickry. And at successor stages, we use this operator A, functor A, P alpha, Z alpha, according to some bookkeeping function. So this abstract iteration theorem works. You need three things to be given. Whenever you're given an initial Q, which is sigma Prickry, a functor telling you what to do at successor stages, according to some bookkeeping function. Then you can iterate this kappa double plus many times with support kappa. And still have, so the point of this theorem is that the sigma Prickriness is preserved. Okay. All right, and now what is our particular application to get failure of SCH together with reflection? Well, the initial forcing given will be EBF. The bookkeeping function will enumerate all the non-reflecting stationary sets, names for non-reflecting stationary sets that we have to kill. And at successor stages, if, so the bookkeeping function, of course, contains a lot of garbage too, but if T dot alpha is something that is not garbage, so it's a P alpha name of a non-reflecting stationary set, then P alpha plus 1 will be given by this lemma from 2 slides ago. It will equal A P alpha T dot alpha, i.e. the forcing to destroy the stationarity of T dot alpha. And then remember the lemma that so then the final extension P kappa double plus, we get the failure of SCH at kappa and reflection at kappa plus. So where do we get the two? So failure of SCH kappa, we get from the very first step. Just the stage 0, like Q already violates SCH at kappa. Now, for the reflection at kappa, how do you argue that reflection at kappa is satisfied in the end? Well, so first you want to argue that for each P alpha, in P alpha, just like the lemma a few slides ago, if a set doesn't reflect, it's one of those sets whose traces are non-stationary. And so in the final extension P kappa double plus, if you had, suppose you had a non-reflecting stationary set, well, this set must have appeared as one of the T dot alphas, where the traces where the traces are non-stationary, and but then at stage alpha we must have forced to destroy stationarity. So in P kappa double plus we get full reflection at the successor of kappa, and actually we get finite simultaneous reflection. So this is for a general kappa high up. And next we wanna bring this whole thing down to earth. So again, what is our favorite singular cardinal? Well, Aleph-Omega, of course. So can we get this result for kappa equal Aleph-Omega? And that's our next theorem that we can. And again, just for a little bit of motivation, why we spend all this extra work then getting it for smaller kappa Aleph-Omega. We'll recall the two classical results of Magidor. So from 77, from large cardinals, one can get failure of SCH at Aleph-Omega, and that from large cardinals, you can get stationary reflection at Aleph-Omega plus 1. And we really wanted to combine the two of them, and it turns out that they can indeed be combined. And this is our next theorem for the particular case of Aleph-Omega. Suppose that there are infinitely many supercompact cardinals. Then there is a generic extension where SCH fails at Aleph-Omega and stationary reflection holds at Aleph-Omega plus 1. Now, so what did we do here? Well, again, as in the case for kappa high up, the main, like the skeleton of the idea, follows the same prescription. You want to iterate, construct an iteration of length kappa double plus, where kappa is your singular, support kappa, so that at each successor step, you kill the non-reflecting stationary set given to you by some bookkeeping function, which enumerates all of them in the end. Now in the next couple of slides, I want to say what were the main obstacles of this theorem that did not appear in the other one. So why is it harder for Aleph-Omega? Okay, so again, we want to start with an EBF type forcing, but now you want to interleave collapses, right? In order to bring, you start with kappa ends leading up to kappa. In the end, you want kappa to be Aleph-Omega. So in the very first stage, you're actually going to force to both make kappa be Aleph-Omega and violate SCH of kappa. Okay. And then again, you want to iterate to kill non-reflecting stationary sets. So the first step is kind of a somewhat newish type of forcing that was donated to us by Moti. And the new ingredient in it is, for people who are familiar with extender-based forcing, is that it used interleaved collapses in the context of long extenders. I'm just going to say this. Oh, well, I'm written it here. Okay. And also, I should have said this in when stating the theorem. When we violate the SCH at Aleph-Omega, this is done while maintaining GCH below Aleph-Omega. So you can think of it as like the ultimate failure of Aleph-Omega, where you have GCH below it, but to the Aleph-Omega is Aleph-Omega plus 2. Okay. So this is kind of the main approach. Now, what are some issues? Well, the very first one, it's no longer the case that, for any P alpha, like at our successor stage, Pn is no longer kappa and directed closed. Well, it can't be possibly, right? Because we are doing collapses, interleaving collapses below kappa to collapse cardinals. So it's not going to be kappa and directed closed. So the way to tackle this lack of directed closure is instead to factor each Pn for each of that iteration at length kappa double plus, to factor it into small forcing followed by a closed forcing. Okay. When I say factor, it turns out that we cannot do it as a product. It will have to be factored as a two-step iteration. So first you factor it into a product, but the product will project into a two-step iteration, which is actually used in a final construction. And also, since just the way the cardinal structure is, you cannot use, you will need to lift embeddings to get that reflection in VPN hole. So we still get reflection in VPN, but we cannot get an actual embedding that lives in VPN. It will have to be in some outer model because of all the collapses we've added. And then there is a lifting argument. And then, of course, we have to show that in order to show reflection in VPN, first you show, you lift your embedding, you show your embedding can be lifted with the right critical point. And then you show that the outer model where it's lifted preserves stationary sets, right? Only then you can use elementarity to conclude reflection. So this was one like a big kind of new obstacle difference between this theorem and the theorem when kappa is just high up. Okay. Because in VPN we only have formerly supercompact cardinals. And of course, all of this has to be preserved under iterating. All right. So, so this is just some of the highlights of the new, how the second theorem for Aleph-Omega really differs from the first. We have to interleave collapses, therefore we no longer have large cardinals in VPN, and the reflection argument becomes harder. Okay. So, I mean, I have only one more slide left on open questions. So it turns out that it's not that easy. I mean, we couldn't figure out how to get finite simultaneous reflection in the case for Aleph-Omega. So in the case when we were getting SCH failing at kappa with stationary reflection at kappa plus for a cardinal high up, it was kind of a, we ended up using like this slick argument having to do with cofinalities of points, showing that if you get stationary reflection, you actually get finite stationary reflection simultaneously. But here, because of all the interleaf collapses, this argument falls through. And right now it is open whether one can get failure of SCH at Aleph-Omega with finite simultaneous reflection at Aleph-Omega plus 1. So, and then we have this kind of a general open question going back to the kind of the more abstract iteration theorem. Well, what other applications may it have? Maybe tree property with reflection, something like that. And there is another question that I should have put, I'm gonna just say it, is, well, what about uncountable cofinalities? So that's also, I mean, at this point, not clear how it will happen. All right, and this is the end of my slide.
Okay, thanks, Dima, very much. Round of applause there. So, so people do please, unmute your microphones and ask questions. Right? Yeah, or you can send them through on the chat as well. But just speak.
I prefer with the voice.
Yes, just speak up, I think.
Yeah.
I have a question. So, Dima, you've sort of hung your results on this compactness idea of combining a compactness property with an incompactness property. And I want to know, do you have a formal definition of what counts as a compactness property or not? Or maybe could you just say a little bit more about exactly what you mean by that?
So it's a very general definition. Compactness property is something where it's a principle where, say, given some object, if it holds for all strictly smaller substructures of that object, then it holds for the object itself. And so it's not more specific than that, but there are some key examples of compactness.
People would disagree with that characterization, though, because they would say compactness isn't just about strictly smaller versus the whole thing, but specifically about finiteness. And so I guess you have a more general
object. Yeah, so I mean, if your object is of size omega, yeah, so this is general because I want, when I think about compactness, I'm thinking something that would follow from large cardinals. I'm thinking of properties like stationary reflection, obviously. Another, at least for me, a canonical instance of compactness is failures of squares. And so, again, this is not a formal definition, but for me, I want, if a cardinal enjoys certain compactness properties, I want that cardinal to, morally be kind of like a large cardinal. But be, so of course, another question here is, can small cardinals, like successors, behave like large cardinals? So maybe when I say compactness, I think of combinatorial properties that when they hold for a successor cardinal, that cardinal in a different life was a large cardinal.
So, I mean, I guess, for example, the SCH would count as a compactness property if you stated it in the form, if the GCH holds up to a singular cardinal, then it holds at the singular cardinal. But I mean, that's not what the SCH says, right? It's just a singular strong limit should have, the GCH holding there. So, but you still regard that as a compactness property, even when?
Not exactly. It's more like I regard the failure of SCH as incompactness.
Okay.
I mean, no, that of course we have SCH in L where there are no large cardinals. But it's so here it's really the failure of SCH that gives you an instance of incompactness. And it's it's very kind of interesting because usually to get compactness type properties at kappa double plus, you need the failure of SCH at kappa. So for example, to get weak square to fail at kappa double, let's say to get the tree property to hold the kappa double plus, you need failure of SCH at kappa. So if you're trying to see, can we force a universe where every cardinal behaves like a large cardinal, then this would require many failures of SCH.
Right. Okay.
But they themselves are like a local instance of incompactness. So it's
right. Okay, well, thanks very much. So I have more questions, but maybe somebody else has the questions.
So you mentioned about the uncountable cofinalities. Has anybody really tried that yet, or is it just open book?
I think it's open, not mine. I mean, maybe Spencer has, you can ask them.
Right, right.
So it will have to be some sort of for uncountable cofinalities. Well, I mean, hopefully some of the ideas here will hold in terms of what kind of sets don't reflect, etc. So for example, if one starts analyzing reflection in, just Magidor's forcing, like vanilla Prickry for uncountable cofinality, you get something very similar in terms of the way to prove that certain sets reflect is by looking at their traces. But now for the iteration, it will be harder to get it. So there are extender-based type forcings for uncountable cofinalities, but then the technicality really increases. So it will be a very nice project, but it's wide open, yeah.
Yeah, so it could be difficult then, yes.
Yes, it could be, but yeah.
So how difficult would it be? I mean, we talk about, here you're making the continuum have size kappa double plus. Is it for kappa triple plus or larger pluses? Is this just not interesting to do because it's...
No, it is interesting, but then your iteration has to have higher length, because if you make, say, 2 to the kappa to be kappa triple plus, the number of stationary sets you have to kill now are kappa triple plus.
Sure.
On the other hand, for cardinal preservation to hold nicely, it seems like you need the support to be kappa and not more.
Right.
And,
so that's an open problem, is it? So that is open then, is it?
It is open. That is open.
Okay.
Yeah, our particular construction would not. There is no straightforward generalization to kappa triple plus.
Right.
So that is open. But yeah, that's true.
Okay, thanks. Yeah.
Mm-hmm.
Anyone else? Or let Joel have another go? Okay, Joel.
Okay, yeah, I just have another question. Okay, so if I've understood it correctly, you first did the argument sort of up high, and then you turned that situation into the Aleph-Omega case, which is, of course, super interesting, by doing the collapse, by interleaving with the collapsing. So how flexible is that to make it happen at other singular cardinals instead of Aleph-Omega if I want it to happen at some other, one of my other favorite singular cardinals, then can I do it, or?
I think so. So for example, suppose you want to do it at Aleph-Omega squared.
Right.
I mean, in a way, I think other singular cardinals would be slightly easier because you have less work to do. I mean, you have less cardinals to collapse.
I see. And what about something like Aleph-Omega 1, or is that, does that not make sense? Or, I mean, it seems.
No, it does make sense. That's precisely where the uncountable cofinality question really becomes interesting. If you can do something like a Magidor style EBF with interleaved collapses at
you have bigger products or something, or more than just omega many kappa n's, right? Or is that what you'd have to do? Or
yeah, and so know that, I mean, in order to do that, so of course you'll be violating SCH at the countable levels too if you're violating it at Aleph-Omega 1.
Oh, right, yeah.
I mean, who knows? Maybe you can even do it so that you have both failure of SCH and stationary reflection.
Oh, all along. That's what I want. Yeah.
Well, I mean, it's almost like if you, yeah. I mean, in general, Magidor style forcings, they project to, I mean, if you cut them off at the omega stage, you get a Prickry forcing.
Right.
Or even if you take like a super compact Magidor style forcing, you cut it off at the omega stage, that projects to a super compact Prickry forcing. So, I mean, I think it's, I don't see any like theoretical reason why it wouldn't be possible, but it will be hard. It's a good project if there is a graduate student in the audience.
Thank you very much.
No, it will be, I mean, it looks like it'll be hard, but yeah, it's very interesting. But we haven't worked on it.
Okay, great. Any more questions or comments from people? No. Okay. Well, thanks, Dima. That was great.
Oh, sure. Yeah, thanks for having me.
Both to hear that talk. Actually, it was very good.
Thank you.
Interesting.
Should I stop? I'll stop sharing now.
If you want.
Let me just announce then that the next meeting is going to be on the 3rd of February, and that's Spencer Unger. It's in 2 weeks, actually. And he's going to talk about stationary reflection at successes of singulars also. So should be interesting.
Well, yeah, thanks for having. By the way, yeah, Joe, is it the same link?
Yes.
Because yeah, maybe I'll log into Spencer stuff.
Okay.
Hear what my competitor has to say. Okay. Yeah, thanks. Maybe I'll wait.
Okay, fine. Well, I guess the room stays open, does it, Sam, until 5:30 if anybody wants to chat. Otherwise, we can say our goodbyes.
Okay, well, and Happy New Year to everyone. Let's hope.
Well, happy
2021 will be better.
Congratulations once more, Annie.